Now we are going to discuss a topic called electric flux. Electric flux is a physical quantity. Okay. So, and it is associated with electric field. So, when I say the electric field, let's write down, suppose there is an electric field lines. Some electric field exists here. In this, there may be a surface. If there is a small surface ds here, small surface ds, and at this point the electric field is E, and electric field vector like this E, then we can calculate the electric flux through this small area ds can be calculated. So, electric flux due to the electric field, the electric flux due to a field E through any small surface ds is given by d phi is equal to E dot ds, that is the dot product between electric field intensity vector and the small area ds. There is a dot product between electric field and ds area, and once you find the infinitesimal flux, from this you want to find the total surface. This surface, this small area I have taken may be a part of surface, so this may be a big surface may be there also. So the total flux in any surface to be calculated, that you have to do the integration of E dot ds. This is the formula for electric field intensity. Now, so now we see that phi is equal to integration of E dot ds over any surface that can be calculated. But if we say that if electric field is constant, if E is constant, and makes same angle throughout the surface considered, if make the same angle throughout the surface considered, then what will happen? E vector can be taken outside the integration. If E is constant, and dot product can be also taken outside the integration if this makes same angle throughout the integration, and we can calculate phi is equal to E dot s. And this can be applied only if E is constant and it makes same angle, theta is also constant. So we saw that electric flux is equal to dot product of electric field and the area vector only if E is constant. But however, this formula we can apply at any time, any situation, that for infinitesimal area, and then integrate the situation and to get the total flux. So we saw that electric flux is a scalar quantity. So its value can be positive, negative or zero. It does not have any directions. Okay? And it depends on what quantity? It depends on, number one, it depends on the electric field. Number two, it depends on the area. And number three, it depends on the angle, orientation of between the area vector and electric field vector. The unit of phi is electric field unit is Newton per coulomb into area is meter square. This is the SI system unit. This is also equal to this Newton per coulomb into meter is called volt. So another unit is volt per meter also. One unit is volt into meter, another is a Newton per coulomb into meter. So here we saw it depends upon the area, and area we know is a vector quantity. Area is a vector quantity. And how we calculate? We know how to calculate area vector. that area vector or S vector is the length vector into cross product between the length vector and breadth vector. If we know this is your length vector, this is your breadth vector there, then the area vector will be the perpendicular to the plane country. This is your surface area. So this surface area whose two sides are this length vector and breadth vector, then the area will be a cross product between the length and b. So the direction may be like this or direction may be like this. They depend upon the right hand screw rule. Okay? So area is a vector quantity. So it is perpendicular to the surface. Area is perpendicular. Area vector is perpendicular to the surface. So suppose if this area vector is there, then I told there will be two normals can be there. This is also normal, this is also normal is there. If the length vector, breadth vector is given, then area vector direction can be calculated by right hand screw rule. But suppose surface area alone is given, then you have to find out this or both are correct. Both are direction correct. That depend upon the situation to situation we have to see. But if you have a closed surface area, in case of a closed surface area, suppose this is a surface area closed, or you take there is a cylinder there, there is a closed surface area, or there is a parallel pipe, there is a closed surface area there. In this closed surface area, suppose you want to find the direction of this, then there are two normals are there, but no need to take this normal, you have to take this is the normal. The outward normal is taken. In case of closed surface area, we take the outward normal is the direction. But here two directions are possible, open surface, but closed surface may usually we take the outward normal. So here so many area directions are there. All are directions of area. So here suppose cylinder is there, for this flat surface it will be outward normal, this flat surface outward normal, this curved surface, this all are the outward normal. Similarly for this is the normal direction, area vector, this right face, this is the normal direction, for the bottom face it will be downward, for left face the direction will be like this and so on. This is the direction of area vector that we know. Let's solve a problem based on this constant electric field. So, what is this one? This is a uniform electric field, and this electric field value is given to us as a 2 into 10 to the power 6 Newton per Coulomb. There is a small square frame such that its area makes an angle. This area vector like this, perpendicular to surface. This area vector makes an angle 60 degree with the electric field directions. Find the flux due to this electric field passing through this rectangular area considered. So all of you pause the video and solve the problem. Now, so what will happen? The flux you have to calculate. We know the flux is equal to, this electric field is constant, so directly we can apply E dot S or E dot area vector can be applied directly. And here this is equal to magnitude of E, magnitude of A into cosine of the angle between E vector and I vector. So if we calculate the side of the east side of this square frame is given as 2 meter. So this electric field will be equal to this electric field vector we know 2 into 10 to the power 6. Area vector will equal to 4 meter square into the square frame is there, and cosine of the angle between 60 degree put then equal to cos 60 equal to half. This cos 60 and 2 get cancelled, 4 into 10 to the power 6. This is Newton per Coulomb, Newton meter square per Coulomb. Now in this question if it says that if the square frame is rotated further by an angle of 15 degree, right on, if the square frame is rotated about this axis, there is my axis there. If it is rotated further about this axis, it is rotated further by another angle of 60 degree was there earlier. It is further rotated by an angle of 15 degree. Then what will be the new flux? How much flux will be passing through the surface area? See what will happen? Now angle of 60 degree. Now you rotate by 15 degree. I have not told it is clockwise, anti-clockwise. I might have rotated like this. I might have rotated like this also. So there are two answers will be there. This may be 16 minus 15 is equal to 45. This is also possible. And another is possible also, 60 plus 15 is equal to 75 degree. So in this case there will be two answers will be there. In one case the flux will be equal to 2 into 10 to the power 6 into 4 into cos 45. In other case will be equal to 2 into 10 to the power 6 into 4 into cos 75 degree. Cos 75 degree. Two answers are possible. Let us solve another problem. The electric field intensity in a region is given by E is equal to 3 by 5 E naught I cap plus 4 by 5 E naught J cap, where E naught is a constant quantity and E naught value is given as 3 into 10 to the power 7 Newton meter square per coulomb. Now question is asking find the electric flux. Find the flux passing through a square frame of side length 5 cm. Passing through a square frame of length 5 cm each. And lying on YZ plane. So pause the video and solve. Again we saw this electric field is a constant quantity. Magnitude, direction both are fixed. So what we need to do is that we can apply directly phi is equal to E dot A can be applied. Now this YZ plane is there and the area is 5 centimeters. So length is 5 centimeters. So area vector is equal to 5 into 10 to the power minus 2 ka whole square is nothing but 25 into 10 to the power minus 4 meter square. And the direction YZ plane is there. So in YZ plane somebody is saying the YZ plane has direction in the along x-axis, because YZ plane is there. So the direction will be y-axis or maybe like this. So it can be either this much I cap will be there or minus I cap will be there, and both there are two answers with that. But if I want to find the mod, mathematical mod of this mod value of the phi, then I can take any one I can take, and this equal to YZ plane. So I equal to I cap suppose take and calculate. So minus will be there, another negative answer will be there. So this vector into I cap. When you have this E dot A 3 by 5 E naught I cap plus 4 by 5 E naught J cap dot 25 into 10 to the power minus 4 I cap suppose I have taken. Then I cap dot I cap is equal to 1, but I cap dot J cap will be equal to 0. So I got 3 by 5 into 25 into E naught. E naught is given as 3 into 10 to the power 7. This much Newton meter square per coulomb. If it is minus I cap, minus answer will be coming. But mod value will be the same thing. This here cancel, call to 5, then 15, 45 into 10 to the power 7 Newton meter square per coulomb or volt meter. This much will be the flux passing through this surface. Let's discuss what is the physical meaning of this electric flux. This flux, what is the meaning there? We have calculated this flux is nothing but dot product between the electric field and the area vector, E dot ds integration, dot product between E and dot A for constant area and a same angle is there. So if this is a electric field, and we know the electric field can be represented by the lines of forces. So in this there are some areas are there. So some area is like this and they have some directions maybe there. So we need to calculate this A into area. When you calculate the E into area, suppose the electric field is like this and you made the area like this, then what will happen? Electric field lines, and we know the electric field intensity is a measure of number of field lines per meter square, or this is not exactly equal to number of field lines. Electric field intensity is proportional to electric field lines per centimeter square. So I discussed that this much is the area there. Per unit area, how much lines of force passes through. Lines of force, I know, is exactly how many number of lines nobody can say, because that depend upon the person who has drawn this one. But the electric field intensity, the number of field lines per unit area, is proportional to this. So when I multiply this, the E the number of field lines per unit area, and I multiplied this unit area, then what effectively I got is the number of field. This flux is nothing but number of field lines. This flux is proportional to, this is proportional to number of field lines, electric field lines crossing the area considered. How many number of field lines crossing to this? This flux is proportional to that one. This is proportional to the field lines. Okay, number of field lines crossing to this. See, let's take an example. Suppose this electric field lines are like this. I put the area like this, then they are passing through this one. But if I keep on rotating about this axis, then what will happen? A situation will come when this area become like this. Now what happened? The lines of forces are grazing over the surface. They are not passing through this one. And in this case, the flux passing through area will be equal to 0, and mathematically we'll see phi is equal to E dot A, EA cos theta. Right now the area vector is perpendicular to surface. Electric field, the angle between them is 90 degree, and we know that cos 90 is equal to 0. So they are not passing through. So it also depends on orientation, how much flux will passing through. The flux, we have heard about this flux earlier also, called fluid flux in the chapter fluid. Suppose there is a liquid is flowing like this, and you put a tube like this, then the liquid will cross through this one. But if you put the tube like this, do you expect that much liquid was flowing through this tube, will the same liquid will flow through this? Definitely not. Or if you put the tube like this, how much liquid flux will be there? Liquid flux will be 0. Here we call the name liquid flux or fluid flux. Here similarly we are given that name of electric flux. Electric flux passing through. So what do we know? The electric flux is proportional to the number of electric field lines crossing the area considered. Whichever area considered, how much electric field lines are passing, it is proportional to that one. This why this electric field is nothing but what is d phi by ds, del phi by del s we can write. So this area we have taken, so flux per unit area is the electric field, or flux is equal to field into dot product of the area is there. This will take the left hand side, cross product will do. So sometimes this electric field is also called as electric flux density or electric flux intensity also. The name of the electric field intensity is the electric flux intensity also, it is called as electric flux intensity. Let us solve another problem. This is a uniform electric field E, and on this I have considered a cylindrical area. Therefore, to calculate flux, physical body is not required. Only some area. Area can be imaginary also. Area can be thought of also. So this area is there. There may be physical body also. Cylindrical body may be present also, may not be there. We have considered an area, cylindrical shaped area we have considered. Electric field is uniform, that is value is E, and the radius of this, the radius is equal to R, and the length of the cylinder is L. Okay, and the axis of the cylinder we know that is parallel to the electric field. So now let's calculate the flux passing through the cylinder. So what are the things we calculate? Flux through the left face, flux through the right face, flux through the curved surface area. Three things we have to calculate. All of you calculate what are the three there. So we'll see for the left face. Let's calculate for the left face. For the left face, you'll see the surface is like this and outward normal will be like this. This is your S1 and the electric field is like this. So the angle between them is equal to 180 degree. So and cos 1 is equal to minus 1. So the flux will be equal to minus E into area is equal to pi r square. Similarly for the right face, right surface, flat surface, if you see the surface is like this, the electric field is like this, and area vector like this also, same directions, the outward normal will be like this. So the theta is equal to 0 degree and cos 0 is equal to plus 1. So the flux through the left face, flux through the right face is equal to plus E into pi r square. Third, the curved surface. For the curved surface, you see this is the curved surface there. This is the outward normal. Here it is outward normal. Here it is outward normal. Here outward. And electric field is like this. So for curved surface, theta is equal to 90 degree. So cos 90 equal to 0. So flux to the curved surface is equal to 0. If somebody asks us to find the total flux, then the flux through the left surface plus flux through the right surface plus flux through the curved surface. So this is equal to E plus E pi r square minus E pi r square and 0. All three will add together. This will come out to be 0. So the net flux in this case passing through this full surface will be equal to 0. If it is a place in a uniform electric field. Let's solve another problem. There is a coordinate system given. We have considered a surface, cubical surface. So, and the cubical surface is my x-axis, this is my y-axis and z-axis. Y-axis and z-axis. And these coordinates are given. One coordinate, this is equal to x is equal to 3 meter. And this is equal to x is equal to 5 meters, suppose. So these 2 points coordinates are given to us. X coordinates are given to us. And it's a square surface, so the length of the square we can calculate with 2 meters there. Okay. Now, question is asking find the net flux through the surface if the electric field in this region, the electric field E is given by E vector is given by 3x I cap plus 4 j cap Newton per coulomb. Three x I cap plus 4 j cap Newton per coulomb. This is my electric field in this region. Okay. So definitely electric field in the xy plane. But see, we have to calculate the flux due to this electric field passing through this surface. We know the coordinate of each point because 2 points I have given, so you can find the coordinates of every point because it's square and each side length will be 2 meters. So we can find the coordinates of each point, and we have to solve this problem. Pause the video and solve it. Right now, again we'll be discussing after you complete solving. Let's calculate the flux through different surfaces. Suppose I say first calculate the flux through the right surface. Suppose I calculate the flux through right surface. So for the right surface, the area magnitude, is equal to 2 meter is the length of each side. So total is equal to 4 meters square. But what is the direction? Outward normal. So the direction will be like this. So the direction is I cap. And for this right surface, the electric field intensity, we know the electric field intensity is not constant, it's a variable quantity. This is equal to 3x I cap plus 4j cap, depend upon x coordinate. And for all the points on the right surface, the x coordinate is 5. So you put this value, this comes out to be equal to 15 I cap plus 4 j cap Newton per coulomb for all the points. So it is a constant electric field case is there. So area vector is known to us, electric field is known to us. For this right surface, I can calculate phi is equal to E dot A. So we know the I cap dot J K will be 0. This I can add the product I can make, and it's equal to 60 Newton meter square per coulomb is the flux through the right surface. For the right surface we calculate. Similarly, we can calculate for the left surface. So flux for the left surface that can be calculated. Left surface can be calculated. Only thing is that here the direction of the area of the left surface is nothing but 4 meters square to there, but minus I cap. So will the flux be, whatever we calculate will be exactly opposite of this? No, because direction is opposite, but here electric field value is different because electric field value depend upon the x coordinate. So on the left surface, every point on the left surface, the x coordinate is 3. So electric field at every point on the left surface is equal to, if you put the value of 3 here, 9 I cap plus 4 j cap meter square. Sorry, this much j cap Newton per coulomb. This much j cap Newton per coulomb. So we can have the dot product of this, and the flux through the left face will be equal to 36, and this other quantity I cap dot j will be 0. So Newton meter square per coulomb. So we got the right surface, we got the left surface. Now is the back surface, flux through the back surface, behind surface, this surface. With the back surface you calculate this flux in the I and J. And what is the direction will be there? Direction will be k cap. The flux surface, for the flux through the back surface, I want to calculate. Then this, I want to get the back surface. I write the BACK back surface. The area vector is equal to 4 meters square the magnitude, that will be equal to outside to minus k cap will be there. So when you have the dot product of this, I cap dot k cap 0, j cap dot k cap will be there because electric field in the xy plane is there. So the flux through the back surface is equal to 0. Similarly, for the front surface also, the flux will be equal to 0. With the front surface also, the area vector in the k cap direction. So we got 4 things we got. One is the back surface, one is the front surface, one is the right surface, and one is the left surface. 4 quantity we obtain. Okay. So now there are 6 surfaces there. Out of the 6 surfaces, 4 surfaces you find out. Now it's the top surface and the bottom surface. I hope you have understood this one. We got the front surface and bottom front surface, this top surface and the bottom surface we'll see. Now let's calculate on the top surface. I will draw only the diagram of the top surface. Okay. So the top surface diagram, if you see, is sorry. This vector electric field, your non-uniform electric field, typical electric field, particular type of electric field. Electric field is given by 3x square y I cap plus y j cap plus x z square k cap whole divided by 3x cube y plus y square plus x z cube Newton per coulomb. This much electric field is there. Find the electric field, find the flux passing through a spherical region. Find the flux passing through a spherical region of radius r centered at the origin. Find the electric flux passing through a spherical region of radius r centered at the origin due to this electric field. For these electric fields, how much flux will pass through this region, that we need to calculate. Non-uniform electric field. All of you take some time and solve this equation. Pause the. Let's solve this problem. So what we'll do, the non-uniform electric field. So you have to take a integration method. You have to do in finitesimal small element. Let's consider here, and let the area be ds. Okay. At this point, electric field, some directions will be there. Okay. Some direction electric field. We don't know direction because direction is variable, magnitude is variable. Everywhere it will be different also. So on this ds magnitude element I have taken, but the area vector direction I know. This is the area vector directions is radially outward, r cap direction. Okay. But electric field may be here. We don't know anything. We will calculate the flux due to this electric field through this surface. So as we know, we can calculate d phi is equal to E dot ds, and this ds vector can be written as ds magnitude into the direction. And what is the direction of ds? This is the r cap. So what I can write that E vector dot ds, what is r cap? Unit vector along the r is r vector by mod r. Okay, so this can be written as, if I put the value of E, this value from this I can substitute here, and I have the dot product of this. So I can write E vector dot r vector into ds by mod r. What is mod r? This mod r is nothing but capital R. So I've written like this. So if I put this two value, E ka value I put 3x square y I cap plus y j cap plus x z square k cap by, I write 3x cube y plus y square plus x z cube dot this r vector, we know this is x comma y comma z are the coordinate. Then we go to x I cap plus y j cap plus z k cap, and there is a term called ds by r. So this quantity we'll see, we'll go to the next page and we'll write down this value. So if you see this d phi, you have the dot product of this and this. So I cap multiplied by I cap, j cap multiplied by j cap, k cap multiplied by k cap. So this will be equal to 3x cube y. This into this will be equal to y square plus this third term xz square will be equal to xz cube by 3x cube y plus y square plus xz cube into ds by r. So beauty of this equation, the way the question is given, after dot product what we obtained and what is given the denominator, they get cancelled out. So what we remain with here is equal to d phi comes out to be equal to ds by r, where r is a constant quantity. So phi is equal to, we'll write integration of d phi, integration of ds by r. Here 1 by r gone outside. So what remain here? ds. What is ds? ds is the magnitude of the small element considered. So if you integrate this, this will come out to be equal to spherical region we have taken 4 pi r square. So 1 r get cancelled. So we got the total flux is equal to 4 pi into r. R is the radius, the spherical region we have taken, whose center is the origin. So for this electric field, what was given, this type of electric field, for this electric field, we calculate the flux that will be passing through our two surfaces, the surface, spherical surface, how much flux will be there. We don't know the electric field direction magnitude, but wherever we put, this will be equal to 4 pi into r. It will only depend if this type of format, the question will be given, always this will be equal to, the answer is 4 pi by r is the answer. So this is the variety of problem that related to electric flux calculations, different with constant electric field, we put this E dot ds, and if it is a variable, that E dot ds integration and calculate the flux. So this is the end of this lecture, and next we'll be applying this electric flux and in Gauss law to calculate electric field of different symmetrical shape body.